So our last portion of chapter 14 that we're going to talk about is pendulums. Okay, pendulums. We gave a couple examples about where we see pendulums in the real world, right? Most commonly in what? In clocks. Most commonly in clocks. But you see it in other places that you might not really think of. Okay, can you think about like at a park? Where would you see a pendulum? Yeah, in a swing set, right? That swing is really a pendulum. Anytime something swings off of your arm or anything like that, that's a pendulum. But we see them more often than we really think. We don't recognize them as pendulums. So there's a few characteristics that have to be true in order for it to really be considered a pendulum or to use the equations that we want to use for pendulums. Okay? It consists of a mass at the end of a lightweight cord. Okay? Why do you think the word lightweight makes a difference here? Why do we care that it's a lightweight cord? Okay, yeah, it would move back and forth better, yeah.
So it doesn't stretch.
Yeah, it doesn't stretch. That's important. The cord doesn't stretch. We want the cord to have the same length every time that it swings. We don't want it to stretch at all. That's right. That's right. We want a lightweight cord that we can ignore the mass of, right? We don't want the cord to be so heavy that gravity is going to be pulling the cord down with a substantial force to throw that pendulum off, right? We just want to have the ratio of the mass on the end of the pendulum be pretty substantial as far as the mass of the cord itself. So the cord could have some mass. It could be kind of heavy, but the mass on the end has to be substantially heavier. Okay, we want that ratio to be pretty one-sided. Okay, so we want a mass on the end. We want the mass of the cord to be negligible, and it's absolutely imperative that it doesn't stretch. Right, we don't want it to stretch because that would affect the length of that pendulum, which realistically affects the period. Okay, and tell me what the period of a pendulum would look like. Is it just one swing? Yeah, it's got to go swing and back. So you'll hear the term to and fro, right? You hear that term before. It has to swing all the way there and all the way back to be considered one period. Okay. All right. So let's look at a couple of these calculations. We had a few of these on our homework yesterday. A pendulum is observed to complete 23 oscillations in 58 seconds. We want to find the period and the frequency, right? And you guys kind of overthought this problem a lot, and it's realistically just a division problem. That's it. Okay? So we want to find period and frequency. Okay, frequency is most of the time measured in hertz, which is essentially an oscillation per second. Okay, it's this many oscillations per this many seconds. So when we're trying to find frequency, we're just doing this division problem, right? Per means divided by. So whenever we set this up, we want our units to end up looking like this, oscillations divided by seconds. So when I set up my problem for frequency, I would take 23 oscillations divided by 58 seconds. Okay, that's it. So when we reduce that down, it's going to end up giving us about 0.4 or 0.396, right? I'm going to round that to 0.4 oscillations per second. So what this is telling us is that every second that goes by, it's made 40% of its oscillation, right? It's done 40%. Okay, and the reason I'm saying 40% is because we're at 0.4, but it's made, less than half of its swing to and fro, okay, or back and forth. When we solve for period, then what's going to change when we do this problem? We're going to flip them. The unit for period is seconds per oscillation. So we would say 58 seconds per 23 oscillations. And when we reduce that down or do our division problem, seconds per oscillation. And since we know it's usually per one oscillation, we can just leave that off, but you can keep it on there as well, right? It doesn't really make a big difference. Bless you. Okay, 2.52 seconds per oscillation. And again, usually we measure it just in seconds because it's per one oscillation. So when we're dividing anything by one, we can drop that off. If we would have found just frequency, could we have solved for period in a simpler way? Do you remember our equation that connects frequency and period? Okay, so we could use either of those equations, right, to solve for period with that. If I would have taken t equals 1 divided by 0.4, what do you get when you plug that into your calculator? 2.5, right? So it's the same thing. Once you solve for one, you can solve for the other, okay? Or you can always go back to your original numbers. We're going to solve for period and frequency of a pendulum specifically. Do these equations look pretty familiar?
Yeah.
Yes, they look familiar, except we don't have the spring constant and mass. This time we have the length of the pendulum and gravity that are helping us pull that pendulum into its motion here. Okay, so you'll need both of these equations on your equation sheet. So these equations allow us to solve for period and frequency of a pendulum specifically, okay, based on the length of the pendulum, which should be measured in what? Length should be measured in what? Meters. Good, meters. And gravity on the Earth's surface is always equal to what? 9.8 meters per second squared. You don't have to plug in negative here. We're not concerned about direction. It's always going to be 9.8. So this equation works for us as long as the cord has a negligible mass, right? We said that it's a lightweight cord, and as long as the amplitude is small. So what would the amplitude of a pendulum look like? Or what would it, how could we describe amplitude of a pendulum? Okay. Right, if we swing it up and it's ended up here, the amplitude is really the degree. Okay, so amplitude is measured in degrees. It's the angle from which that pendulum has been pulled from its axis point. Okay, so the amplitude would fit right in here. It's an angle. Okay, so on a pendulum it looks different. Amplitude looks different. On a spring, an amplitude is a measure of distance, right? How far that spring has been stretched or compressed. On a wave, your amplitude is also the height of that thing. So amplitude for a pendulum looks a little bit differently, but it's an angle. Okay, it's an angle measurement. So this equation works for us as long as the amplitude is relatively small, right? When we hit about the 35 degree mark in terms of our amplitude, we're pulling that pendulum up really far. It can affect our period just a little bit because our mass could kind of fall out of that cycle. It could just look a little bit differently. But as long as our amplitude is relatively small, right, usually within that 30 degree range either way, our period is not affected. And we're going to look at that tomorrow in our lab, actually. But most of the time, amplitude is not going to affect it. Mass is not going to affect it. They don't even go into our equation to solve for period. So amplitude and mass really have no effect on our on the period of a pendulum as long as they are within reasonable range, right? If we pull our pendulum all the way up to 90 degrees, do you think it's going to fall in a very smooth pattern? No, probably not, right? It's going to be, it's not going to be smooth. It's not going to have a repetitive pattern. It's going to fall kind of clunky, and it's going to swing for a little bit and then die, right? All right. Does the mass go into our equation anywhere? No. Okay, so just because a mass was given to us does not mean that we need to put it in there. Okay? Don't put things into an equation that you don't need. Right? We're just looking at gravity. We're just looking at the length of the pendulum. The length is measured in meters, which is what we want, so we don't need to change anything there.
Two
0.42, and do you know what the units are?
in the centillions or whatever.
Oscillations. Oscillations per second, or otherwise known as hertz.
I got a question.
Uh-huh.
Why is it 9 is always a decimal place?
Because 1 over 2 pi is very different than 1/2 pi. Okay, those two things are not the same thing. Where is pi in this equation? Is it in the numerator or the denominator? In this situation, it's in the numerator. That's not what our equation tells us it's in. Okay, in our equation, it's in the denominator. So it's not 1/2 times pi, right? If you plug in 0.5 times pi into your calculator, you get 1.57. If you plug into your calculator 1 divided by parentheses 2 pi, close parentheses, you get 0.159, right? So those are two very, very different answers. Make sure that you're being consistent there and being kind of adamant about doing that in your calculator correctly, because a lot of people plug in that 1/2 pi, and it's not the same thing. 1/2 pi is not the same as 1 over 2 pi. Okay, does that make sense? Okay. Did everyone else get it to come out about 0.42? Okay, so if you see yourself 1.57 and 0.159, they're about 1 decimal place off. So if you find yourself being about a decimal place off every time, right, that's probably the problem, is that you're doing that 2 pi division incorrectly. Okay. All right, the pendulum has a period of 0.98 seconds. What's the length of the cord? Okay, this is the exact same thing. We have to divide 2 pi over first. So when you put 0.98 divided by 2 pi into your calculator, it's either divided by parentheses 2 times pi or divide by 2, divide by pi. Okay, I know you feel like I say that every 5 seconds, okay, but it's because it's still not being done 100% correctly. Oops. Okay, so we divided by 2 pi, we squared both sides, and then we ended up multiplying by 9.8 to get that by itself. And our L came out to about 0.24, 0.238 meters. Yeah? Yes? No?
Yep.
Okay. So I'm going to make a question here real quick. Okay, so let's say that we have a frequency of 2.68 hertz and a length of 1.5 meters. We want to find what's the acceleration due to gravity at this point, right? Where's this pendulum at? We're going to find the acceleration due to gravity here. Okay, so this might be that there are pendulums not on the Earth's surface. And we're looking at solving for G. All right, so if we solve for our acceleration due to gravity, we're taking it multiplied by 2 pi, then squaring both answers, and then taking it by 0.15. Okay, multiplied by 1.5. So we get a gravity equal to 425 meters per second squared. So is this probably on the Earth? No, right? This is on a planet that's much bigger, mass-wise, and much smaller radius-wise. This isn't even on Earth. Okay. All right, so we're going to review waves here a little bit. And when we draw waves, it's important that we have the wavelength concept correct. And a lot of us were having our waves basically twice as long as we need to, right? Wavelength has to be where it goes up and down and back to the starting point within that wavelength. So let's say for our first problem, we have an amplitude of 2 units and a wavelength of 6 units. Okay? So wavelength means it's got to go up and back down in 6 units. So I'm going to count over here. 1, 2, 3, 4, 5, 6. And I'm going to just mark that. Then I'm going to count another 6. 1, 2, 3, 4, 5, 6. Okay, I'm just going to mark those. Oops. Okay, because I know that's where I have to be back to my starting point. My amplitude is 2 meters. Or 2 units. I'm going to assume that each of these boxes is 1 unit. Okay, so that means my height that I'm ever going to go is here. The lowest I'm ever going to go is here. Okay, you don't have to draw all this stuff. I know it's going to cross the center line there. Okay, and that kind of helps me think about it's got to go up 2 units, it's got to cross, and it's going to go down 2 units, and it's going to come back. Okay, so whatever my wavelength is, I'm going to cut that in half, and I know that's where it has to cross the center line at. Okay? What? It's got to be up and down before you get back to your original. So again, I'm going to cut this in half, and I'd go up, down, and back to my original. Okay, so whatever your wavelength is, cut it in half, and you know that's where you got to cross the center line before you can come back. Okay, does that make sense? Okay, we had a vertical spring with something attached to the end, and it said this was stretched a total of 65 centimeters. Okay, then it said when a different mass was added to it, it was stretched a total of 85 centimeters. Okay, but the thing is, we don't know like where the equilibrium point was. We don't know where the spring would be if no mass was attached to it. We don't know any of that. But what we do know is that there's a change in the spring when this new mass was added to it. Okay, there was some change in our spring here. And I think this was about 5.6 kilograms. And I think this one down here was 8.16 kilograms. Okay, so there was a change that made this spring stretch even further. Okay, so we don't really know what was happening up here, but we do know what happened in this little portion of our spring, right? So we're trying to solve for the spring constant. Okay, so this is how I would go about that. We're going to look basically only at the change that happened in this spring. Okay, so this change right here. How far was the spring stretched when that new mass was added to it? 20 centimeters, right? So our new displacement is 20 centimeters or 0.2 meters. Okay, that's what our displacement is when this new thing happened. What was the mass change that made it stretch that extra 0.2 meters? How would I find the mass change?
You minus the final line.
That's right. Final minus initial. So I take 8.16 minus 5.6. That tells us that 2.56 kilograms made that spring stretch this extra 20 centimeters or 0.2 meters. Okay, is that part making sense? Okay, so if I want to solve for my spring constant, I'm going to say F equals Kx. What force is causing this thing to stretch? Gravitational force. So I'm going to use this mass that I know has added to it. 2.56 times 9.8 equals K times the change in displacement when this mass was added to it. So 0.2 meters. Okay, is that kind of making sense? All right, if we don't know what was happening at the beginning, we do know what was happening during the change. So that's what we're looking at here. So 2.56 times 9.8 divided by 0.2. One more time? Okay. I got K equal to about 126, okay, or 125, roughly around there. Newton divided by meters.